Good evening, everyone. Welcome to Science at the Theater's New Light on Dark Energy, brought to you by the Friends of Berkeley Lab. My name is Jeff Miller, and I'm Head of Public Affairs at the lab. The program will unfold as follows. We'll have the moderator make a few opening remarks, and there will be 3 presentations by the Berkeley Lab scientists. There will be some conversation among them between their presentations and at the close. Then we will open it up for questions from the audience. We know that there will be a lot of questions. We ask that you keep them brief, no speculation about the origins of the universe. If you want to talk about that, you can post to our Facebook page afterwards. On June 6th, we'll also be back at the Berkeley Rep, but at the smaller stage, with our topic will be nanoscience. We will have 4 outstanding young scientists on the panel that evening, so we hope that you can join us for that. With that, I will turn the evening over to our moderator, Andy Fraiknoi. Please welcome him.
Wow. First of all, is this on? Okay. What a crowd, my goodness. Excellent. So first of all, I'm Andrew Fraiknoi. I teach astronomy at Foothill College, and I work at the Astronomical Society of the Pacific, which is a public education organization in astronomy. I'm the moderator, and we have 3 very distinguished panelists. Let me introduce them one by one. Greg Aldering, who's on my right, your left, did his undergraduate work at MIT, where he really kind of went below the cosmology level and discovered some asteroids before he saw the light and went on to bigger things. He has his PhD from the University of Michigan. He was a Carnegie Fellow and now is the project leader for the Nearby Supernova Factory project. And indeed, he discovers exploding stars for a living, and we'll talk much more about that during the program. He was co-recipient of the 2007 Gruber Prize in Cosmology, which is sort of our poor man's equivalent of the Nobel for cosmology. And then in the middle, Shirly Ho has her undergraduate degree from Berkeley, an institution some of you may have heard of. But she got her PhD, good applause in the audience, her PhD in astrophysical sciences at Princeton. And she has been moving in a steady arc from physics to astrophysics to cosmology, so to bigger and bigger subjects. Currently, she is a Chamberlain and Seaborg Fellow at the Lawrence Berkeley Labs. Shirly Ho. Your groupies are in the audience. This is good. And then last but not least, Eric Linder got his undergraduate degree at Princeton, his PhD from Stanford, and he is co-director of the Institute for Nuclear and Particle Astrophysics at the Lawrence Berkeley Labs, and also deputy director of the Berkeley Center for Cosmological Physics. Eric is the author of a respected textbook called First Principles of Cosmology, and in his spare time, he writes parody songs about dark energy. So Eric Linder. Great. Now, someone's going to do the slides for me while I do the introduction. So the way we're going to do this is I'm going to give a little introduction tonight to the general astronomy subject. I should ask that perhaps. How many of you have had exactly 0 college-level courses in astronomy? Excellent. Okay. How many of you have had 1 college-level astronomy course? Okay. How many of you have had more than 1? Okay, you're not supposed to be here, but we'll let you stay just tonight. Okay, so to get everybody started, I'm going to give a little introduction. Then each of our panelists is going to talk a little bit about his or her work. Then we'll have a discussion among ourselves, and then we'll open things up for questions from the floor. So I just want to, if we can have the next slide. I want to introduce our subject in the next slide. I want to talk a little bit about the universe, so we're all, pardon the expression, on the same wavelength here. We astronomers like to divide the universe into 3 realms. There's our home, the solar system, which is sort of our immediate neighborhood. Then there's the galaxy, our city of stars, and then there's the universe at large. So let's go to the next slide. This is our solar system. Currently 8 planets and a lot of miscellaneous stuff. Sorry, Pluto fans, only 8 planets. This is the sun, our star at the left, surrounded by a variety of worlds. And this is the home base in which we live. Now the next slide takes you a little bit further out, and now we see the enormous pinwheel of stars, which are our home city of stars. So the sun is one of at least 200 billion other suns, stars, that make up a giant island of stars called the Milky Way galaxy. And this is actually not a picture of the galaxy, it's a painting, because it's hard to take a picture of the galaxy. We're in it. It's like trying to take a picture of yourself from inside your kidney. I don't know if you've tried it, but it's messy. So this is more a diagram of our Milky Way galaxy, an enormous pinwheel of, as I say, hundreds of billions of stars. And one of the great discoveries of modern science is that our Milky Way galaxy is just one such city, one such island of stars, and there are huge numbers, billions and billions, as a famous astronomer used to say, billions and billions of other such islands of stars. The next slide. Before I show you that, though, the next slide shows you what happens inside these galaxies. So very important for our discussion today is the notion that stars are not forever. Stars are born, they have a lifespan, and they die. So here you see a star birth region where you see a beautiful cluster of young stars in the middle, the bluish cluster, and then the womb of cosmic raw material that gave birth to them is opening up, revealing the fresh, young, adolescent, bright stars in the middle. So we still see new stars being born. Stars go through long lives, and then at the end of their lives, stars die. Many stars die peacefully, but a few overachieving stars actually blow themselves to pieces at the end of their lives. And the next slide shows you that. It's really nice that nature puts an arrow right there before the star explodes so we can actually see which one's going to blow up. But this is actually not in our galaxy, but in a nearby one. But there's a star which was living its regular life, and then one day we woke up to find the star having blown itself to bits. And these explosions are quite dramatic, quite bright. Sometimes they're so bright we can see them rivaling the sun in the daytime sky. We think this happened in 1054 AD, a little before my time, but some of the older administrators at Berkeley remember this. But in 1054 AD, there was such an explosion, and this one was seen in 1987. We call such exploding stars a supernova. And the next slide shows you my bumper sticker. They really are. And because these are incredibly bright, the explosions which signal the death of a massive star can be seen far, far away. And you'll see that's a crucial part of our discussion tonight. The next slide then shows you a different galaxy, not our own, but one not too different from our own. If we could see ours from the top, we would see a graceful pinwheel of stars, much like this one, again with billions of stars blending their light together. The next slide shows you that stars come in groups and so do galaxies. Here you see a cluster of galaxies, a collection of galaxies, and these galaxies sometimes interact. You see a rather personal moment of interaction right here, but because there are young people in the audience, I won't pursue that one. Even though the galaxies sometimes gather together in groups, there are many different groups scattered around the sky. And the next slide then shows you the big discovery that was made in the late 1920s and early 1930s by Edwin Hubble, which is that these enormous galaxies of stars are not sitting still, but they're moving away from us. Except for the nearest ones, which are waltzing with us, they are all moving away from us. Not only that, but there's a pattern to their motion. The further the galaxy, the faster it's moving away. Say that again. The further the galaxy is from us, the faster it's moving away from us. Was it something we said? But this was an enormous discovery. It's called the expanding universe. And we had to then find a theoretical framework to explain why this was happening. And the next slide shows you Albert Einstein on the right, whom you may recognize, and Georges Lemaitre, a Belgian priest, on the left, who were the two theorists who put this together for us. It was Einstein who showed that space and time were stretchy and malleable, which is part of our discussion. But Einstein was too chicken to have an expanding universe. Einstein actually introduced a fudge factor into his theoretical description of how the universe might work, because he thought the universe, any decent universe, should be sitting still. And it was Lemaitre who first showed that it was possible to have Einstein's stretchy, malleable kind of universe of space and have it expand as well. And we now accept that the universe was expanding and that this expansion is a built-in feature of the universe. And that the beginning of the expansion was a very hot, dense event, which we call the Big Bang. And when the Big Bang happened, it was not, as many people think, an explosion in empty space. This is the mind-boggling part, so get ready to have your mind boggled, okay? We don't think of it that there was this huge emptiness and bing, there was a Big Bang. We think of the Big Bang as an explosion of space, of time, of matter, and of energy. Right. So that when the Big Bang happens, space begins to expand. Space stretches as the universe expands. And we actually now see the expansion of the universe, the moving away of the galaxies, not so much that each individual galaxy wants to get away or has a rocket motor on it which wants to drive in some direction, but that space itself is stretching. And the next slide shows you the idea with an analogy. If you have a balloon where there are little specks representing the galaxies, then you can see that if you blow up the balloon, if you stretch the balloon, then the little specks on the balloon get further apart. I don't know if this has kept you awake at night, but when you blow up a balloon, where does new balloon come from? Have you worried about this at parties? Maybe if you smoke. No, I can't say this in Berkeley. But when you blow up a balloon, where does new balloon come from? It stretches out of the old balloon. And you don't have a nervous breakdown over that. That's perfectly reasonable, right? So imagine when space stretches, new space stretches out of the old space. That's the way we're currently thinking about the expansion of the universe. The next slide shows you then Penzias and Wilson, Arno Penzias and Robert Wilson, two radio astronomers at AT&T Bell Labs, who in the mid-1960s discovered that they could actually find the afterglow, the leftover flash of the Big Bang, this hot, dense state of the universe where everything was more together. And they were able to show that this afterglow, this flash, this background radiation, as we now call it, fills all of space, as we would expect the leftover energy of the Big Bang to be doing. And we're going to look during the discussion tonight at this leftover radiation, the flash of the Big Bang. They got the Nobel Prize for that. The next slide now shows you our big issue here. So you have this expanding universe, the Big Bang threw everything apart, and what's going to happen in the future? That's the past. Now we look at the future. Well, there's one other factor that we thought we needed to consider, which is gravity. Gravity is not just a good idea, it's the law, right? So what would gravity do to all the stuff? Can I use that technical term, stuff? All the stuff in the universe. Well, gravity is the pull of all stuff on all other stuff. That's the technical definition. And so that means that if there's gravity in the universe, the gravity of the galaxies will tend to slow down the stretching of space to make them come together. Depending on the strength of gravity versus the energy of the Big Bang, we'd imagine that either the stretching would slow down but never stop, or it might even stop. That's what we thought a decent, self-respecting universe would do. But in fact, what people like Greg and a whole group of people around the world are discovering is that it's much different than we expected. Our last slide in my sequence tells you the story that we are in a runaway universe. What has been discovered is that instead of slowing down, the stretching of space is speeding up, accelerating. And this is ridiculous, right? No universe should behave like this, but if it does, there must be another factor, something that's causing this acceleration of the universe. And what that factor is, how we know that the universe is running away, is in fact the subject of our discussion tonight. So that's my introduction, and let me now... Don't encourage the jokes. Now let me introduce Greg Aldering, who's going to talk to us about how exploding stars are going to make this, how they make this discovery possible.
Well, thank you, Andy. Good evening, everyone. So tonight I'd like to give you some insight about how we have used supernova to discover that the universe was accelerating and how we will use it to figure out what the dark energy is that is propelling that acceleration. Here, just to start, is a little whimsy. This was the cover of Science magazine celebrating the discovery of the accelerating universe. It has Einstein blowing universes out of his pipe. Unfortunately, that version of dark energy, that model really has not held up. I'm going to spend most of the time describing supernova and how we've used them. So this example of one of these galaxies that Andy told us about, and supernova occurring in those galaxies. And I'm going to try to help show that although dark energy is a very mysterious and complicated subject, keeping cosmologists very busy, it takes a lot of detailed work to make the measurements. The underlying principles are pretty straightforward, and I want to relay some of those to you this evening. And it looks like one of my slides is missing. Yeah. There, I'll go this way. So here, there's just three basic principles that I'd like to go through. The first is very intuitive to most people. This shows a series of luminaria winding up a sidewalk. And as the luminaria get further and further away, they get fainter. So when we compare the brightnesses of nearby luminaria to distant luminaria, we can tell which ones are further, which ones are closer. And this we can apply now to things in the universe if we're able to compare the brightnesses of nearby and distant objects. Then there are two other things that people may have heard about, but maybe don't have an intuitive sense for. One is the fixed speed of light. So light can only travel at a fixed speed. And what this means is that when we look at these more distant objects, we're looking back in time. The universe is like a time machine. And so we're not seeing them as they are today, but as they were when the light first left them. And so this allows us now to look into the past of the universe and see how it looked even billions of years ago. In fact, we can see back close to 13 billion years altogether. And then we take advantage of a consequence of this stretchiness of space that Andy referred to. So when the space is stretching, when light is coming to us, that light has a wavelength to it, a certain rate at which it oscillates. It gets stretched too. This is referred to as a redshift. And the amount by which it stretches is exactly proportional to how much the universe stretched from the time that light was released to the time that we measured it. And so this gives us a very easy way to measure basically how much the universe has stretched at various points in the past. We can put that together into what we call the expansion history of the universe, which is what tells us that that expansion is speeding up. So I got my slides a little bit out of order. Let me now go to this one to discuss the tool that we're going to use. Okay, we don't have luminaria or nice light bulbs that say 100 watts on them. But we have these tools that nature has provided us, the supernova that Andy described, which are so bright they can be seen over vast distances. And although they don't come with a wattage label, we've also figured out how to determine how bright they are. So this, in the upper left here, is an artist's conception of the particular type of supernova we're interested in. It's called a type 1a supernova. I won't get into the details of why it's called that. And you might think this big fiery red thing is the supernova, but actually it's a tiny little star buried in all of this gas that it's accreting from the fiery neighboring star. That type of star is referred to as a white dwarf, and it's about a tenth of the size of the Earth, even though it's as massive as the sun. So its matter is very compact, and in fact, it has no way to generate fuel currently, and the only thing that keeps it from collapsing completely is pressure from the electrons in that white dwarf. So if it's living there by itself, it'll just continue to cool, and this will be the ultimate fate of the sun. Another 5 billion years, the sun will turn into a white dwarf, and it'll start to cool off slowly. But this guy's in trouble because its companion is adding to its mass. So it's trying to fight gravity and not collapse. When you add a lot of mass, it's hard to fight gravity. And when this star gets to be about 1.4 times as massive as the sun, its temperature becomes unstable. Now, rather than collapsing, it'll actually go ahead and blow up. And let's see if I can actually get my movie to run here. Okay, there we go. So this, again, is now a computer model of such a star blowing up. And it starts, as I said, with a size about the tenth of the size of the Earth. And in 5 seconds, it gets as big as the Earth. In a period of about 4 hours, it could traverse the distance between the sun and the Earth. It's blowing up at a temperature of close to a billion degrees. And when it's doing that, it's generating a lot of chemical elements too. And I'll describe those in a little bit. So now we want to go. Okay. So this is what we could see if we could really see a supernova up close, the artist's impression, the computer calculation. But of course, we never are that close to a supernova. In fact, we really don't want to be that close to one. It'd be rather dangerous. So the question is, what do we see from Earth? We've already seen the nice, pretty picture of a supernova, and this would have been a case of showing a supernova brighten and fade away in this galaxy over here. So what we see from Earth, besides just a nice picture of the supernova in its galaxy, is the energy that gets released over time. So the supernova actually starts very faint, becomes brighter, reaches what we call its peak brightness, and then fades away over time. And these supernovae are somewhat interesting because part of the reason it's getting brighter, of course, is this big ball of fire that we saw in the previous simulation is getting bigger and bigger. But on top of that, normally that would make the gas cool, but there's radioactive nickel in there that is keeping the gas really hot. And so that's why these supernovae achieve such remarkable brightnesses. So for instance, when it's at its, when you take all the light that it gives off over its lifetime, that's about as much energy as our sun is going to release in its entire lifetime. So this is a period of a few weeks, about 2.5 weeks to rise, a few more weeks to fade away. In a few weeks, it gives off as much energy as the sun will in its entire lifetime. Or at a given one point, it's giving off as much energy as a typical galaxy, so roughly as bright as an entire Milky Way. This is really what allows us to see it over very vast distances. So this one runs by itself, good. So one of the things we have to do, we have these potential tools that we can see to vast distances, but a bit of the work has been in learning how to actually discover them. So Andy referred to some of the naked eye supernova that we're seeing from Earth. Those occurred once every few centuries, and that's what's typical in the galaxy. is a supernova like the ones we're interested in, will go off once every few centuries. So you can't just sit on a galaxy and wait for a supernova to go off. You'd have to have a lot of fortitude in order to do that. And so the way they originally found is someone might have been looking at a galaxy and noticed, oh, well, there's a new star there. And what would typically happen, of course, is that they would have found it after it reached its peak brightness, and it was very hard to get any scientific information out of it in those cases. So it's a bit like whack-a-mole, where you're waiting there for the mole to pop up, but your mallet gets there too late to be effective. But like whack-a-mole, of course, the right way to play the game is you monitor all the holes where the moles might pop up their heads, and you look for the supernova there. So astronomers got somewhat good at that, but because it takes so long, hundreds of years to find supernova in one galaxy, they had to develop the capability to monitor thousands of galaxies at once. And that became possible in the 1990s as we made bigger and bigger cameras to put on telescopes. We could look out into the universe, take a picture. One picture might have 1,000 galaxies. We'd spend a night, get tens of thousands of galaxies, and we could get to the point where we had supernova on demand. And that was really the birth of using supernova for cosmology, because now we could be ready with all of our telescopes to follow up on those supernova discoveries and make the measurements of the brightness and the redshift that we need in order to apply those basic methods for determining the distances. And this is just another example now of searching, in this case with the Hubble Space Telescope, so scanning over little patches of sky looking for the supernova. And here's an example of some of the supernova discovered with the Hubble Space Telescope. So these are from a search that was done by a group at Lawrence Berkeley Lab. So in the centers here, you can see these tiny, faint little dots are the supernova. And you can see that they're a lot brighter when they're close by. So the closest ones are here. In this case, it's right on a galaxy, so not easy to see. And then they get fainter as you go further and further away. And this most distant one here in this sample exploded when the universe was about 40% of its current size. So what we found with the supernova in 1997, 1998, is we had supernovae that were somewhat more nearby than the one shown here. And we found that those were fainter than we expected. So if we go back to our basic principles, if those are fainter than expected, they're further away than we expected. And so they exploded longer ago than we expected. And that means that basically the universe was expanding faster than we expected at sort of these intermediate redshifts. And this was a sign to us that although it was expanding at a rate we expected long, long ago, around the time of the Big Bang, the subsequent to that, about 6 billion years ago, that expansion started to speed up. And that was our basic discovery. Supernovae were too dim. The expansion of the universe is accelerating. When we interpret that in terms of Einstein's relativity, then we have to have some term in there like this cosmological constant that Andy noted that Einstein had put in. At the time when he missed the discovery of the expansion of the universe, because he put the fudge factor in and Hubble discovered the expanding universe, Einstein called this his biggest blunder ever. But now it's actually this thing that we don't know what it is, gives the best description of the brightnesses of the supernova. But as Eric will discuss, there are many more exotic possible explanations for why this acceleration is speeding up. So let me just summarize here a bit. We're able to see the supernova over vast distances, and that's really key. Nature could have given us a tool that was much dimmer. This work could have taken another century longer. So we're just extremely fortunate that there are such objects. They give us the expansion history of the universe. The other part of the equation, besides their just being out there for us potentially to observe, was getting very good at finding them. And we also then discovered that the expansion is speeding up because of the overly dim distant supernova. And one thing that I would have mentioned a little bit just in terms of the future if one of my videos had worked, is besides that nice light curve showing the release of energy over time of the supernova, they send us actually a much richer stream of information that shows us all the chemical elements that are in that supernova, how fast they're moving, these types of things. And this is information that we hope in the future will allow us to measure the distances to supernova much better than the 7% distances that we're able to get right now. Thanks.
So you've heard a little bit about how we discovered the accelerating or runaway universe, how these signposts called supernovae have shown us that. But one experiment for something this radical is not enough. So we had hoped that there would be another way of showing that the universe is behaving in this odd way. So our next speaker, Shirly Ho, is going to tell us about how we get soundings of this kind of runaway universe using another technique. So Shirly, go ahead.
Thank you. Thanks. Hi. Thanks, everyone. I will be staying a little bit on this side of the stage since Greg was on the other side and the computer is here in case there's any technical problems. I apologize for any of that in advance. But first of all, and most importantly, thank you all for coming. I did not expect this turnout, and this is amazing. 600 seats all filled up in the whole auditorium. So roll the theater. Thanks. I'll be talking about, in particular, how to use this very exciting new technique called Baryon acoustic oscillations. I'll explain what it is very soon. But basically, you look into the sky and use this mesh of galaxies, this huge number of galaxies. And I'll be looking into this mesh of galaxies and look for the longest yardstick, in my backyard at least. And you'll be like, well, do I have a longer yardstick than mine? And here's just how long it is. It's 470 million light years long. And that's the longest yardstick I would claim I can use to measure the expansion of the universe. More importantly, you can measure this expansion universe at different distance, farther and farther away from us. So at 300,000 light years away, 3 million and 3 billion, all the way. And the experiment I'll be talking about in particular is called Sloan Digital Sky Survey 3. A part of it is called a BOSS, this huge acronym, but basically it just means we're looking for this longest yardstick in the universe and try to see how long it is as we see it at different parts of the universe to measure the stretchiness that Andy was just talking about of space and see how we can go about understanding what Einstein might have made the biggest blunder of his life. So here it goes. But before we go further than this first slide, I will show you how we go about mapping all these galaxies. And it is the first time I myself have seen a telescope. So you'll be joining me with the first time I'll see a real telescope on site. And it's moving. This is the Sloan Digital Sky Survey 3 telescope. It's opening for the night to work. And I actually was just way down there. I'm the one wearing the white hat. It's a very important part of my life. It's the first time seeing a telescope as an astronomer. And this single telescope has mapped over a quarter of the sky over last century. And it's not just providing the great data sets that we have to work on understanding what Einstein has maybe made a mistake. Is the universe running away? Is it expanding? How fast is it expanding? Not just that, but also made this great movie, as very important movies, that as we imagine if you have a lot of money and decide to build a spaceship and shoot very fast away from Earth, and you're taking a movie all the way back, looking back to Earth. And that's actually what I'm going to show you. Every single one of these images are real. They're real images of the galaxies, of every single one of them. We look out from Earth. So every single one of them, they're real. They're not making up any simulations at all. And you can slowly see that there are structures in the universe. There are large clusters. We call it large cities. Well, actually not cities, large metropolitan cities of stars. Those are large clusters. And there are large voids. Voids, there are nothing in there. there are all these amazing structures of the universe. You spin around, and you see more of those, and you go out further. These are the black holes, sucking all the dark matter exotic particles, all the baryons, protons, neutrons, all you know. And then we hit this background radiation that Andy just mentioned that they discover the afterglow after the Big Bang. And that's what we actually see. This is 300,000 years after the Big Bang happened, this afterglow that we all know and love. We call it the cosmic microwave background. And every single dot there, this color code, the red being very hot spots, and the blue spot is being cold. Every single one of them will grow into clusters or voids that I mentioned earlier, into the galaxies that we see nowadays. And I will mention basically how to use, we've jumped back a little bit for the movie, that picture, this mesh of galaxies. How do we actually go about learning about stretching of space, learning about expansion of the universe today? So that's my introduction for what we're supposed to learn. So now the technical part is more or less finished. We can go to this side of the hall. And this part, it says, well, what do you do with this mesh of galaxies? I have the data now. I'm sitting in my office looking at the computer. What can I do to understand the universe? So what you do is to calculate something called the correlation function. Hold on, don't be too worried. This is actually a very simple idea. It's to look at how one galaxies correlate with each other. And from that, I'll explain even more later, we'll look for the longest yardstick, which is this 470 million light years long yardstick, and look at the size of this yardstick over different distances away from us. And this sounds really hard. I'm like, well, don't you guys think that's hard? I mean, I think that's what's hard when they first explained it to me with this picture. So, and that wasn't too long ago. And so I decided that as a physicist, I say, okay, how should I explain it to everyone? Not just to myself, but also to others who might be interested. And I wrote down an equation, of course, and I was like, okay, that's a little hard. Yeah, boo, yeah, I agree on this one. And I decided that as someone who would like to calculate correlation function, what do we want to know, right? Can we maybe calculate the correlation function of everyone? Say, you're a galaxy, you're a galaxy, you're a galaxy. How do you correlate with each other? Can we do something like that? So I decided to look at an average American family. That's my impression. You can blame it on me. It's nothing to do with Berkeley Lab, just my impression of American family here. I decided that maybe mom and dad goes to work every day. So they go to work. So you go to work, or maybe your kids stay at home, and the pets stay at home too. I forgot about the dog, actually. And the mom and dad goes really far away. Well, how far it is? So if you look at the public transportation database, and they said, actually, everyone commutes about 22 minutes on average. And if we all commute 22 minutes, which means you'll commute, say, 20 miles approximately, depending how fast you drive. I drive a little bit faster than that sometimes, and that will be farther, but say 20 miles. So we commute 20 miles away from home every day. So now let's take a correlation function glasses and put it on top of my head, and I realize if you look at where you are during the daytime, you'll be either 20 miles away from your kids, and if you're a kid, like I'm at school or something, and my parents will be about 20 miles away from me. So if I go to every single American family and try to calculate, well, where are you, and how far is your family member from you? That's 20 miles away, right? And calculate that and add up all these correlation functions. How correlated am I from my family member? Then you calculate the correlation function of the population of every one of you guys. This is a toy model, so don't take it too seriously. But you see a bump at 20 miles right there. And that's what it means by we're correlated. There are more people about 20 miles away from you, basically, during daytime. And surprisingly, if you're a galaxy, galaxy does similar things. They also have a bump, but except that's 400 million light years away. This longest yardstick I was talking about, this number that I've been repeating over and over again, is about 25 trillion times of the distance between us and Earth. That's really long yardstick. That's the bump that I was talking about earlier. And it wasn't because they're commuting. Well, they're not really commuting. The galaxies aren't commuting this time. But some early physical processes actually push the galaxy to very, very far away. And that's the distances that we're talking about. And I'll be hopefully showing you how exactly this works. But for now, just think about it as just being the galaxy's driving away from home, and it ran out of gas. It stopped. And it kind of stayed there. And that's the correlation function I'm talking about today. And this distances is fixed. We know exactly how long this yardstick is supposed to be. So if I put this yardstick at 300 million light years away from me, or is it 100 million light years away from me, I can measure how long this yardstick is in appearance to me. And thus, you can measure the expansion of the universe. Is it open? Is it flat? How fast is it expanding? You can all just look at the yardstick, similar to what Greg had talked about using those standard candles, but now we're using this standard yardstick, a big one, I would say, but it's not too hard to use when it's so large to actually observe. And I'll show some small animation here to hopefully illustrate the physical principles. I mean, there are no gas and there are no cars for galaxies, of course. And how does it actually work? Here is the picture of the universe at 300,000 years old. And each hotspot and cold spot corresponds to one of these peaks of matter, including the dark matter particles that you guys might have heard about, including the protons, the neutrons that we're more familiar with, and the electrons. And as the temperature goes down, so for now, the photons are with the electrons together. They're interacting, they're good friends. And then, at some point, they're only good friends because I think the photons think the electrons are quite hot. So that's why they're really good friends with each other. They're going hand in hand. The photons are really moving fast, so it's pushing really hard on the electrons. And the electrons going really, really far away from the center, right? And since the electrons are charged, and so it drags along the protons with them, right? So it drags along everyone, and that's why there's this wave. It's like the pebble dropped in the pond, and then this wave going out. And that's this Baryon acoustic oscillation. That's where the acoustic come in. But then, as I said, the universe cooled down. It's not so hot anymore. The photons were like, well, the electron's not cool, well, not hot enough anymore, so I don't want to hang out with him at all. So the photons free stream. They left the electrons. And thus, they kind of get stalled. There's no more gas. That's what I was saying. The photons are not pushing the electrons anymore. And thus, the protons and the electrons, everyone stayed at that radii from the center. But you're like, well, there are many, many pebbles. As we saw from this picture, there are many, many little over-densities, we call them, extra matter or under-density, where less matter. So well, how does it work? It's not just one thing, right? Just like your family, we look at one correlation function of everyone, not just for one family, but many, many American families. So if we look at many, many of them, that's what happened. So all these little matter clumps were actually getting outward, and it got frozen because the photons just left the electrons all alone because it's not hot enough. And that's how this works. And finally, we find these fluctuations of the size of 470 million light years large. And what I said earlier, I'm just going to repeat it, is that we have a yardstick all the way from back here And then we can measure a yardstick at this distances away from us, and measure the same yardstick, and here is closer to where I observe, and you can map out how the whole universe expands, all the way to as far as you can find galaxies, or maybe we can use black holes. There are things that we just started learning, is that anything that traces the mass is all game. And that's how we look at all the expansion of the universe. Thank you.
Let's give that to Eric. So let me see if I can summarize where we are. So we've heard a little bit about the idea that we learned that the universe was speeding up from observations of these exploding stars. Now your yardstick confirms this, confirms the idea that the expansion history of the universe, which can be read from these observations, is not what we expected, but that the universe is speeding up. And the question that, of course, occurred to us when we asked ourselves, how come this is happening, is what could be the cause? What else do we need to introduce into the universe to make it possible for the universe to be speeding up instead of slowing down? So now we're going to turn to a theorist, someone who can then talk to us about the idea of why such an acceleration might be happening and what kind of factors might be responsible. So let me now introduce Eric Linder, who's going to talk to us about the theory of the runaway universe.
Okay. So Andy makes it sound very, very rational and measured that, theorists go out and they explain things. Whereas when you talk to the experimentalists, they'll think of theorists as these wild-eyed speculators out there. There's this famous saying, to explain the acceleration of the universe, the cosmic speed up, it takes a crazy idea. But then the caveat to that is not every crazy idea actually is the right idea. So a theorist is supposed to be thinking of crazy ideas, but then it has to be checked with the observations and checked for internal consistency. If you think about it, we're really stretching here. And by stretching, I don't mean the stretching of space-time. I mean, what we're trying to do is understand the universe as a whole. We're trying to understand, you heard, things over billions of years, over vast distances. And you might almost wonder, is this hubris to think that we can actually understand the universe? How do we go about actually understanding these elements of physics? And we're actually familiar with other instances of this. How do we learn about things when we can't go out there and touch them, when we can't have them in the laboratory, when we can only sense them from a distance? So if we have the question, for example, is the climate of the Earth warming over time, we can't go back to the year 1800 or 1500 or 2000 years ago and take a thermometer and measure the temperature. We have to rely on relics. We have to rely on evidence that comes to us. And so one way of doing this, for example, is you look at the growth patterns in tree rings. The tree preserves a record of its environment, the way it was at that time. So we're looking back into the past as we look deeper within a tree. And so something about how did the tree grow? Was it only grow a little? Does that mean maybe it was a very cold year or a very dry year? Did it grow a lot? Maybe that tells us how wet the year was, how warm the year was. We learn about the environment through these relics. And that's exactly the things that you've heard about from Greg and from Shirly. We're using the relic light, basically, that comes to us, whether it's from the cosmic microwave background, whether it's from the exploding supernovae, or whether it's from the galaxies. And so just as we had these tree rings, they're using these measurements of supernovae and galaxies to basically measure what the environment of the universe was like at those very distant times in the past. How quickly was the universe expanding? Was it slowing down? Was it speeding up? And so forth. So that's what they're doing. And then, as Andy said, we can then take that evidence, take that data, and try to figure out how does that fit in within our theories, within the elements that we know about within the universe, within the laws of physics that we know about, or do we have to stretch our understanding of those laws and those elements? And so this has been done many times before when things have puzzled us about the universe. So again, Andy started off with our home, the solar system. And we didn't always understand the solar system the way we do now. So for example, in the 18th century, when the outer planets weren't known, people observed the motions of the planet Uranus, and they realized it did not accord with their ingredients and their theories. So the ingredients were, well, they knew all the other planets out to Uranus, and they had their theories, Newton's law of gravitation, which had worked extremely well for over 200 years, and yet Uranus wasn't moving in the right way. And so the big question was, do I need to add a new ingredient into my universe, or do I have to change my theory? And the answer turned out to be, we have to add a new ingredient. We have to add a new planet. And you could actually predict, assuming that the theory, Newton's theory was right, you could predict where should this new planet be. And it was actually discovered in that location. Neptune was discovered in 1846. And therefore, the theory was fine. We just had to add a new ingredient. Another puzzle came around, again, as observations got good enough, in the inner solar system. Again, the orbit of the innermost planet, Mercury, didn't accord with the ingredients and the laws. So within Newton's law, within the planets that we knew about, again, the motion of Mercury was just a little bit off. And so people said, oh, okay, we know the answer to this. We learned that from the outer solar system. There must be a new ingredient. There's a planet inside the orbit of Mercury that's changing things. And they looked and looked, and they couldn't find anything. And then it took Einstein to come along and say, suppose your ingredients are fine, but we have to stretch. We have to extend our laws. Newton's laws are very good as far as they apply, but when the planets are moving very quickly near a very massive object, they have to be tweaked a little bit. We have to go beyond Newton's laws, and he came up with general relativity. And so that turned out to be the answer for the 19th century problem. We needed a new law. The ingredients were fine. We needed general relativity. And so the puzzle we're faced with today is when we see the speed up of the universe, do we have to add a new ingredient, a new type of energy, or do we actually have to tweak the laws of gravity, now tweaking Einstein's laws? And so that's the real big mystery that excites me, excites a great many physicists. And the wonderful thing about this is the little tweak we have to make is actually not so little. So this shows a sort of pie chart of the total amount of energy or energy-like stuff in the universe. And the stuff that's like us, the familiar stuff, turns out to be less than 5%. And so that's one thing that's just completely amazing, that the stuff that we're used to, atoms, light, neutrinos, if you've heard of that, all of that stuff fits into 5%. That there has to be some other new stuff, which actually we've known about since about the 1930s that it had to be there, called dark matter, that has to reside within galaxies and within clusters of galaxies. So that has to be about 25%. But that stuff acts normally under gravity. It actually binds things together. It attracts things together. To speed up the expansion, we need some new stuff, which is just sort of given the name of dark energy. Something that has to act opposite to gravity, that has to pull things apart. And again, it's not a little tweak. We're talking about 70% of the universe that we have to figure out what it is. And so that's a big step forward. And that's, again, what the supernova data and what the galaxy data is talking about. The big discovery that was made here in Berkeley some 13 years ago in 1998, that you needed the 70% of the universe to basically explain what's going on. But we still have this mystery. Do we have to change the theory of gravity, or do we have to add a new energy to it? And so let's start off with the idea of adding a new component the way we had to with the outer solar system. What are the possibilities? Oh, OK, I'm not quite up to that. So let me go back to this idea of stretchiness of space-time that Andy and, in fact, all the speakers talked about. What we're used to seeing is gravity attracts objects. If you sit on your bed, the bed goes down. The mattress, the sheet on the bed gets a depression. If you then put a little ball on that sheet, it's going to roll toward you. It's going to feel that curvature, and it's going to roll into the hole. Okay? That is basically what Einstein said gravity is, that the attractive force is due to the curvature of space-time, this stretchiness of space-time. And a black hole is when you take this really, really far down, so when something falls in, it doesn't come back out. If you have no energy around at all, then the sheet is just flat. Nothing is on your bed. Something's just flat. You put a ball down there. It's just going to sit there. It's not going to roll one way or the other. So then, as a theorist, you always like to think of strange things, and you say, well, is there ever a situation when I can sit down on the bed and the bed comes up in a hill instead? And that would clearly be a very strange type of matter, of energy, something that acts opposite to the way that gravity normally does. But if you think about it for a while, you could actually come up with something. You could say, suppose I had a long straw, and I suck through the straw, the sheet's going to come up where I have the straw near the bed. It's going to make a hill. And so a sort of suction, what a physicist would call a negative pressure, can actually create this sort of situation. And so that's what dark energy is basically equivalent to, this negative pressure. And so you still have the stretchiness of space, but it's a negative pressure stretchiness. So that's one possibility for what the answer could be to cause the acceleration. So we have to look for things that it would have very negative pressure. So stretchiness itself has a pressure. You stretch a spring, it wants to pull back together. It has this stretchiness. And so Einstein came up with this idea that maybe the stretchiness of space is such that it exists everywhere. Every bit of space is equally as stretchy as every other bit. So this is basically the cosmological constant that was alluded to by the speakers before. But again, we can think of something a little bit stranger, and we could think of where the stretchiness of space is different from different parts of space to another part of space, and that it's dynamical. It changes over time. So in the early universe, it wasn't having much of an effect, but right now, it is having a much larger effect. And so this is a different type of ingredient. One would be Einstein's cosmological constant. Another would be this sort of dynamical dark energy, which varies in space and varies in time. And this is sometimes given the name quintessence. In magazine articles, you might have read about dark energy as quintessence. We don't know which of the answers this is. And we also don't know if maybe it's not a new ingredient at all. There is no planet inside the orbit of Mercury, but it's a change in the laws. What we want to do is explore and find out. And I really like this quote from Dr. Seuss, where you have a school child who's so proud at learning his alphabet and says, I know all the letters from A through Z. And then one of his friends comes over and says, only through Z? There's all those letters beyond Z, and there's all the animals that go with them. So On the On Zebra. It's a great book if you haven't read it. It's a good physics book. If you want to be a theoretical physicist, definitely read that book. Okay? So he has the quote that the friend of the school child is saying, you'll be surprised what there is to be found once you go beyond Z and start poking around. But for a physicist, once you go beyond Einstein's cosmological constant, which has the Greek letter lambda instead of Z, then you're going to find all sorts of really strange physics. And that's one of the exciting things, is trying to figure out what part of the physics it is. Or again, a new law. So let me talk now a little bit about, suppose the ingredients are fine, but we have to change the law of gravity. So gravity is strange. Gravity is different than any other force that we know about. For one thing, gravity is always attractive, okay? Or at least we thought it was up till now. Gravity is also really, really weak. If you go up the campanile and you drop a coin off, which I don't advise you to do, I don't recommend you to do that, that coin is pulled by gravity all the way down, all the way down. It hits the ground, it's dropped. I don't know how high the campanile is, let's say 100 feet tall. It drops all the way down, and then it just stops right away when it hits the sidewalk. It doesn't drop another 100 feet through the earth. It stops within much less than an inch, a small fraction of an inch. Why is that? Because gravity pulled it all the way down, but then the electromagnetic forces within the sidewalk, the things that make this solid, even though atoms are mostly empty space, that's electromagnetism there. Electromagnetism is so much stronger than gravity that when it falls all the way through, it doesn't matter. It stops right away once it gets within the range of the electromagnetic forces. So you can start thinking of crazy reasons. Why is gravity so much weaker than electromagnetism? So we know space has 3 dimensions. Okay? I can demonstrate 3 dimensions here very easily. Okay? And you can add time in as a 4th dimension. But suppose we look at the sort of field lines, basically how strong the electromagnetic force is within the space. Instead of drawing it in 3 dimensions here, I've drawn it in 2 dimensions. You can see there are a lot of field lines within this little 2-dimensional slab, meaning the force is very strong. But suppose I then pull some of those field lines out into another dimension, a dimension that if you lived in this slab, you couldn't see, you couldn't access. It's just some extra dimension. Then the field lines are much more spread out, and living within this slab, I only see a few of them. So I feel a much weaker force. And so some physicists have thought maybe gravity is basically that situation, that it feels extra dimensions that the normal forces can't feel. And so again, it's a crazy idea. Not every crazy idea is true, but maybe it is true. We don't know. So the idea is that there could be hidden dimensions, more dimensions to space than the 3 dimensions we know about. That would be an example of how you would change the laws of gravity, the laws of physics. And so the idea is everything, all the normal physics operates in this sort of membrane. Physicists, for obscure reasons, abbreviate it to brain. So you might have heard of brain worlds. That just means a membrane, like the surface of a drum. Okay? Everything lives within that, but gravity can leak out into the rest, into these hidden dimensions. And that's what makes gravity weaker. Moreover, it can weaken over time. And so the motion of this brain within this sort of higher dimension, I like to just call the sound of one hand clapping, put a little bit of zen into it, that maybe the part of the physics is actually saying we have to learn about higher dimensions. We have to sort of go into different ways of thinking. So if gravity weakens over time, then basically that is apparent in our dimensions as basically a acceleration of the expansion relative to what we think it should be if gravity stayed the same strength. And so it could be an explanation for this accelerating universe, in that you don't have a physical dark energy, rather you have a change in the laws of gravity. And as a side note, if gravity is changing over time, then in the future you're going to weigh a lot less. You'll have to wait a few tens of billions of years to notice it, but still, it's a weight loss program, so maybe I can patent that or something. So how do we actually figure out, do we put a new ingredient in, or do we change the laws? So we have our observations, and the great thing about having these two very different sorts of observations is they will actually predict slightly different things. So here's what I call a cosmic battle. The stretching of space, this acceleration, keeps galaxies apart, and it prevents galaxies from clustering and forming big groups. Okay? So if you have the picture that Shirley showed of the family spread out, imagine that the land is now suddenly expanding. It would be very hard for that family to get back together. So the expansion is pulling things apart, prevents large structures from growing, whereas gravity wants to pull things together. So the picture over here is instead of using physical forces, I'll use social forces. You have a big group of friends here out at the mall or whatever. They're all standing at the bottom of an upward running escalator. One friend's a bit late. The social attraction wants to pull that one friend down to the big group, wants to form a larger group, just like gravity does. But the space in between is stretching. He's trying to go down the up escalator. And so that prevents that growth. And so you have this battle between the gravitational attraction and the expansion of the space in between. And how quickly this group grows depends on that sort of cosmic battle. So again, the supernovae are measuring the expansion rate very well. Shirley was talking about these galaxy surveys, showed that beautiful movie of flying through the galaxies. How quickly those galaxies cluster and grow together measures the growth, and then figuring out which one wins, what the rate at which the structure can grow up, allows us to test, are we talking about a new ingredient of dark energy, or are we talking about a change in the actual force of gravity? So we're on the brink. A number of times people talked about the technological advancements. What do you need to discover these supernovae, to measure this incredibly long standard ruler, the standard yardstick? And we're really on the brink of developing new types of surveys. So Shirley's movie showed you one early version of this where we can start to map things in 3 dimensions. When you look out at the night sky, you see the stars, you just see positions. You don't really see how far away the stars are. The technology is getting good enough that we can now do these massive surveys where we can get this 3-dimensional information very quickly. And here at Berkeley Lab is actually one of the world centers for developing this sort of 3-dimensional scanning, 3-dimensional mapping of the universe. And so the picture that I show here is you have a pond. The pond is really 3-dimensional. But from a distance, all you see are the patterns of light, the patterns of the sunlight that are projected on the bottom of the pond. So that's like the microwave background patterns, the blue and red hot and cold spots that we see. We can learn a lot from it, but if we could actually map out the pond in 3 dimensions, from the sunlight above to the leaves on the surface and floating within to the bottom, we can learn a lot more. So we're basically at the beginning of an astronomical revolution, going from a 2-dimensional map of the sky to a 3-dimensional map. And then I love this M.C. Escher picture, which is actually called 3 Worlds, which exactly captures this concept. So here he shows the trees up from above the water, reflected in the water, and then you have the fish living below the water. You're getting these 3 worlds all coming together, and you can really learn quite a lot by doing this. And so as we map in 3 dimensions, we're going to reveal an enormous amount about our universe. But as you've heard throughout this, we still have a lot of questions, a lot of things to discover. And so that's why I think all of us here, and obviously you for showing up tonight, are really excited to think of the explorations that await and the things that we're going to learn. Thank you.
So we're going to have a little bit of a discussion among the 4 of us now, and then we're going to open things up for your questions. So if you are thinking about questions, please make sure that you're thinking questions and not statements, okay? If you have your own theory of the universe, we'd like to hear about it later. What we want to talk about now are questions for our panelists. But let me, as the moderator, begin with a couple of questions, and everybody jump in as you want to. One of the things I want to ask each of you is, what's the most exciting for your work in the future? What do you look forward to in the next decade that will help settle some of the questions you were talking about? So, Greg, maybe we can start with you. Can you tell us what's the future of the supernova work, and what are you looking forward to?
Well, there are a couple of things. One of the things is, I alluded to at the end of my talk, is really learning enough about the supernova to improve the precision where we can measure distances. And the very nearby supernova are the ones that we really can study for that, and the project that I'm leading is looking into how to do that. And we've started to make some progress there. We're also looking forward to future telescopes, both in space and on the ground. So there is a plan that NASA has for something called W-FIRST, with the stated aim of trying to measure the dark energy equation of state. It's not really within the decade time frame, unfortunately, very expensive, but those types of things, basically new measurements of very distant supernova and obtaining much higher precision with the supernova. And what we really want to go to on the experimental side to give the theorists something to ponder is to see whether the amount of dark energy has just been the same throughout the history of the universe, or whether it's changing. And right now, things agree pretty well with Einstein's cosmological constant, but we're actually starting to be able to make measurements that aren't just silly measurements. They're actually starting to make some constraints to show whether it's changed or not. And so those are things that we're really looking forward to in the next decade.
So let me see if I understand this correctly, and then I'll ask Shirley and Eric the same question. But one of the things that I hear you saying is that this is separate from the issue that at the beginning it looks like the universe was slowing down, and then we switched over to an acceleration. Now you're saying that even within the measurements of the acceleration, we may be able to tell the difference between Eric's springs that are always the same way and those that are dynamic. That's
right. It's extremely difficult measurement because, for instance, the springs that Eric showed can come very close to looking like the cosmological constant. So depending on one's worldview, which in particle physics, there's really not a good theory for the cosmological constant. There are many, many theories that could explain potentially what we see, and so people want to really probe those. Some people may be content with, well, we'll accept Einstein's fudge factor and live with that. But from a physics point of view, There's no reason why that should be there. And when people have tried to predict it, they're off by a tremendous amount. It's been called the worst prediction in all of physics. So that's really bad. And so people really want to go beyond Einstein's cosmological constant.
All right. So Shirley, I'm going to ask you the same question. If you were thinking ahead for the next 10 years, what's exciting you about what's to come?
Sure. I would actually like to say that Eric has mentioned an experiment that's led by the lab here that's planned for the next decade for making this 3D map, this three-dimensional map of the galaxy survey even bigger, going way back beyond, say, half the age of the universe. And having this 3D map of galaxies, we will measure not just the dark energy, but maybe if gravity is really modified, well, modified in our case means maybe Einstein was really wrong more than one way, then maybe we can explain what we observed. And that's for the galaxies. So the second part of my answer is we want to use something new. This is something we have sort of recently developed called Lyman alpha forest. But basically, these are backlights lit up by black holes, really, really far away. And as you might remember from my movie, the black holes are so close to the afterglow of the Big Bang. It's way back, like when the universe is really early. And you can use the black holes with its, eating all the matter, its accretion disk is zooming in with all this huge amount of matter pouring in, and there's light coming to us. And we can use this light to light up from all the way from the quasar, we call it quasar, from the black hole, to us. All the little mass in between them, we can actually map them out. And to use those, instead of each single galaxy, this city of stars, we can actually look at the expansion of the universe all the way back to much earlier time of the universe. And that's what I'm excited about.
Right. So just so we make it clear for the audience, the black holes you're talking about are not the kind of black holes we hear about that are made from a single star. These are what we call the supermassive black holes, the ones that form in the centers of galaxies and where the black holes might eat millions or billions of suns worth of material. And that's how come even far away we can see evidence of their eating. Right?
Exactly.
These are not small black holes, but giant, really horrible black holes that are being overfed, and so we can see them at a great distance. And you're thinking of using those as probes of what the early universe was like.
Exactly.
Good. Okay. So now, Eric, let's talk about what you're looking forward to in the years to come.
I think the main thing is really to actually start to get some of the answers. So as Greg and Shirley said, to actually go out and get the data. So this is a long process. You have to come up with the concept of these new instruments. You have to figure out how to make them work. You have to get the telescope time. You actually have to get the data. And then a theorist will go and write a paper in a day and come up with 10 different ways of explaining it. But as a theorist, I'm in awe of the fact that we actually can go out and measure things in the universe, that we can be quantitative and actually decide between these many theories, which might all appear equally beautiful, but only one of them is going to actually be right in our universe. And that we've actually developed the ways of going out, making these three-dimensional maps, seeing these supernova all the way across the universe, and being able to map out that sort of tree ring picture of the history of the universe. It's just wonderful to think that we can actually come up with ways of knowing about our universe.
Okay. I think one of the things that really impresses people when we have a discussion like this who are just new to the subject is that slide that you showed, which is I think, worth mentioning again, which is that all the matter that we are made of and that the Earth is made of is less than 5% of the universe. And then there's something called dark matter, which we really haven't talked about much in this program. And then 70% of the universe is this whatever is accelerating the universe, which we're calling dark energy as a code word, but we don't know if it's a change in laws or a new ingredient in the universe or whatever the heck it is. So I want to ask each panelist to if you wish, to talk a little bit about how this notion that everything in the familiar world is such a tiny part of the things we're talking about affects you as you do your work. Do you think about this? Is this something that makes you feel creepy in the middle of the night? Or is it something that's exhilarating and you're thinking, wow, now we're really going to get some new pictures, new answers to the way the universe works? Does anybody want to comment on the feeling of this weird picture?
Well, I'll just say that there's always a tension for scientists, right? They would like their theories to be able to explain everything. So if we could explain everything neatly, we'd like that. On the other hand, there's a spirit of adventure that now we have all these things that we don't know to go and learn about. But I guess I'm long past the idea of really being creeped out by it. And I know that when I first heard about dark matter, I probably had a similar reaction to what people feel when they look at dark energy. But eventually when you see how overwhelming the evidence is that there's something interesting going on, you get beyond the sense that this is like the ancient Greeks making circles and circles and circles to explain the behavior of the solar system, which is what they did. They had a not too bad model of the solar system. It was completely wrong, but
because
stood for centuries. Yeah, they put the Earth in the century. So a lot of scientists, I think, view this as another Copernican revolution, and we're, instead of sort of hitting ourselves over the head for being dumb because we don't know what it is, we're all excited because we're going to try to find out.
Okay. Other comments from the panel?
Okay.
Yeah, I mean, personally, I think it's wonderful both how closely we're tied to the universe and the fact that there are things beyond us. So the idea that all the atoms in our body come from the centers of stars. They basically come from supernova explosions. They were created, all the heavier elements, the carbon, nitrogen, oxygen, were once at the heart of stars. So we have this intimate connection to the universe. And yet, it's great that the universe is actually even bigger in thought than that there are these other materials, these dark matters, dark energies, and so forth, which is completely different from us. I think we're sort of having it both ways. We're having the best of both possible approaches that way.
So I actually was lucky in some sense because being born in the 80s means you go to college where people already established the fact that there is dark energy, dark matter, and you came in realizing, well, we just need to figure out what they are. And these might be, for me, actually would be like hints to maybe theory of everything, how the biggest and the smallest should actually be ruled by the same physics. And I think that's where the connections between particle physics and cosmology are bridged. And maybe, hopefully, even though for me, maybe that's not for my generation, maybe next generation, to figure out how these black holes, where all these things are really small and dense in there, versus the space that's so wide, where the critical density of the universe is about, a gram per or actually an atom per centimeter cube. And it's so different scale. They should be all ruled by the same rules. Why do we have so many different forces? Can we put them all together? And maybe something that different, that's special, like dark energy or maybe dark matter, would tell us something very different. So that's my approach to it.
All right. Well, let's now thank our panelists again. And we have 4 microphones set up, 2 in the balcony and 2 down here. So there's already a line at microphone number. How did you know that was microphone number 1? Very good. So there's already a line at microphone number 1, but there's plenty of room at the other microphones. And if you have a question, we encourage you to go to one of them. I'm going to go around the microphones in a democratic way. And then I'm going to ask the panelists to raise your hand, essentially, if you want to answer that question. So unless you're specifically asking a person, I'm going to throw it open to the panel. All right, so we'll start with microphone number 1, gentleman in the red shirt.
Thank you. This is for Professor Fraiknoi and your balloon model. I have no problem with blowing up the balloon and having the space expand, but when I do that experiment, the spots that I've painted on the balloon to represent the galaxies, they expand too. So isn't the space inside the galaxies expanding just like the space between them? It's always been a puzzle to me.
Okay, so actually I'm going to use you as an object lesson. You're not supposed to ask me questions. I'm the moderator. You're supposed to ask the distinguished guests questions.
Oh, well,
so,
they can all answer it, but it was to respond to one of your points.
I appreciate your following up on one of my slides. So does someone want to answer that, or should I? What?
I'll give it a try. So, yeah, the big difference there is that within something like a galaxy, gravity overwhelms that stretching of space. Just like our solar system is kept together by gravity, or the atoms in this room are kept together by molecular bonds. So it's just a question of which things are going to win out. And so your dots indeed on your balloon expand because there's no differentiation between what they're made of. They're all made out of the same material and basically subject to the same forces. But here in a galaxy, gravity is strong enough to pull things together, just like if the universe were dense enough, it would pull the whole universe together and stop this accelerated expansion.
So my teacher said in graduate school that if you don't want to imagine the spots on the balloon expanding, think of the galaxies as little coins taped to the surface of the balloon, and you know that money doesn't expand during inflation. All right, moving quickly to the microphone number 2.
Hi there, thanks. Yeah, this is just a practical application question. My Hindu friend informed me recently that the universe is in its final stage of expansion and will soon contract. And this is what I've learned today is sort of contrary to that. And just in sort of a scientist to non-scientist language, how might you start a conversation like this in a friendly way, saying that dark energy is, well, that's not really going to happen? How might you do that?
What would you say to someone who thinks the universe is going to collapse soon rather than expand?
Well, I would actually say that in the past, like 20 years ago, there are models that says the universe will actually collapse. Greg's group and the people at Berkeley and there are other people actually are the group who figures out that the universe are expanding with accelerating rate. Otherwise, it would actually collapse. So I think you could totally talk to your friends and say, well, there's one possibility, but what the observations recently told us, it's going to expand and accelerate even more. That's it.
Thank you.
All right, we'll go to microphone number 3, up there.
Can there be reverse black holes, like if there's a black hole that instead of eating stuff, it barfs everything it sees out?
Good question. Could there be a reverse black hole which, instead of eating stuff, throws things outward? Who wants to tackle that?
It's a good one.
Okay. So there is a theory, we haven't observed it, that there can be what are called white holes, basically the opposite of the black holes. You can even, Einstein, in fact, had a theory that the things that get sucked into a black hole, that it could be basically a bridge to another part of space-time. So rather than it just being a dip in space-time, it's actually like a handle. It dips down, and it comes out at another part in space-time. The things that get sucked in one place could be emitted, burst out in another place. We've never seen that, but it's theoretically possible.
Sure. We need to turn, no, they're turning things on and off so we don't get feedback. So wait a second, let's turn Shirley's microphone on and you're ready.
Yeah, so I would just add that actually the book by Stephen Hawking has talked about this extensively, that there could be the white hole, and it's completely possible. Actually, when I was a little bit older than you were, I actually read that book and found it fascinating. And that's why instead of going to making movies like Star Trek, I'm sitting here.
All right, we'll go to microphone 4 over there.
Thank you. Wonderful presentation. Thank you very much. I just want to mention that Dr. Alex Filipenko is my first-round draft choice on my Cosmology fantasy league, so I really appreciate everything that you guys are doing. Mine is actually a two-part question. First, I'm a little concerned by the notion of this repulsive force. Today, I'm concerned about that, this repulsive force that equates to this dark energy, because that's a brand new force. We haven't seen anything like that. We don't have this repulsive force, but we do have gravity. I think that, like what we're saying here, it might be a new element. Now, we've also seen in the last couple of years, Koszaliński is talking about this dark flow and these massive structures outside the observable universe. So why couldn't large, massive structures outside the observable universe account for some of the acceleration of the universe? And that's the sort of the first part of my question.
Okay, we need to turn on the microphone. Okay, go. It concerns physicists as well, this idea of... Yeah? Is your microphone on? Okay, can we try it again? Okay.
Okay. So the idea of a new force, as I think Greg said, a theorist would love to be able to explain everything with what they start off with. That's the first thing that they try to do. But then when we have new observations that conflict with that, we then have to look at deeper levels. As you said, it could be that there is no new ingredient, no new dark energy, that there's simply an expansion in our understanding of gravity. And that's certainly a good possibility. As far as things outside the universe outside the visible universe sort of pulling on things, you would have to explain why it's pulling equally in all directions, why it is happening now as opposed to early on where we actually saw the slowing down, saw the deceleration of the universe. You also need an immense amount of mass to be able to do that. So it's not generally favored as the explanation that you would go to first.
So, with all due respect, there's so many people waiting.
Okay, just a second.
I'm going to go on to the next person, and if each person can only have just one question, I'm sorry, but otherwise we'll never get done. So, microphone number one, we're back to you.
Yeah, I'd like Eric to go on a little bit more about the idea of the quintessence, about how currently the universe, the rate of expansion is increasing, and if I understood it correct, that you might be saying that in the future, perhaps the rate of increase might go back down again. And if that's the case, how would we confirm that? I mean, the lifetime of, say, human civilization is so much shorter than the lifetime of the universe. How would we be able to figure out if that's actually going to happen?
You got it? Okay, good. Right, so yeah, quintessence is a very attractive idea. Again, we would like some definite evidence. We'd like to see some property of the quintessence rather than just saying, well, it fits what we currently know. We would like it to predict something. Could it change in the future? Because it's dynamical, the way these springs bounce around, it could behave differently in the future. Until we actually come up with the physical theory that explains it, we won't be able to know what it does in the future. And so we won't be able to definitively predict what the fate of the universe is until we really have a physical understanding. And so we not only need the observations currently and in the past, but we need that understanding to go with it to predict the future. So in a similar way to the tree rings with global warming, we not only need to know what's happened in the past, but we need to understand what causes the climate change in order to then predict how it will happen in the future.
All right, and we'll go to number two.
I have a question for Greg, and it's how many supernovas are discovered each year, and is there any speculation to how many supernovas you don't see?
Well, so the number discovered a year has changed a lot in the last few decades, but now it's easily several hundred a year that can be found. Most of them are found nearby, but there are also surveys going on with large telescopes that monitor certain patches of sky. Those ones that are going on looking for distant supernovae are looking at just a tiny fraction of the sky, probably something like 1/10,000th of the sky. So if we could monitor the whole sky, we'd see far more. We wouldn't see 10,000 times as many because we really can't see the supernova that are hidden behind our Milky Way galaxy. But easily something like 5,000 times as many. And there is actually a plan for a big telescope, the Large Synoptic Survey Telescope, that will survey the sky from Chile, and they will find many of these supernovae. One thing that we've learned is to get past it's very exciting finding supernova, but then one has to be able to make the right measurements to use them for cosmology. And so there's actually a huge winnowing down from the ones that are found to the ones that we can actually use to measure relative distances. And so of all the supernovae that have been discovered, which is at this point tens of thousands of them, the number that we can use to make a measurement like the one I described is something like 800 supernovae. So that's another thing we'd like to improve on getting more of those, but we're really actually at a stage in our measurement where if we could just measure those same ones more accurately, we could get as much knowledge about dark energy in that way.
Great. So just to be sure that everyone understands, there are several types of supernovas,
Yeah.
what you're saying, and only one of them, the one you call type 1A, are the ones that are regular standard bulbs where you can see them like your lumina and measure distances with them. That's what you're
saying. And people are trying to use some of the other kinds, but even so, for instance, as I mentioned, if we get there too late and we can't measure its peak brightness, then we really can't use it for this type of measurement.
All right. Good. So now we're up to number 3.
So it was very interesting tonight to learn about some of the efforts underway to learn more about dark energy by looking out into the universe, vast distances and grand scales, supernovae and things like that. But if whatever dark energy is supposed to stand for consists of 70% of the universe, it seems like it should be all around us and maybe observable at some level, at a more local scale. So I was wondering, curious to know about if there are efforts underway to try to learn about these forces, maybe through particle physics.
Well, sorry.
Sure.
Well, I would first say that, there is a huge experiment called LHC, the Large Hadron Collider, that's trying to look for dark matter on Earth. Well, not just dark matter detection for everywhere, but actually trying to create the particle itself that could be dark matter. That's one way from the particle physics side. But then it's also the dark matter detection, that they have detector for possible dark matter candidates on Earth to try to detect them directly. So there are a lot of them going on in particle physics field too.
And any hope of getting local evidence for dark energy?
Right, so Shirley was covering the 25%, which is obviously a good fraction of the universe that you want to deal with as well. The 70% dark energy, even though it's a huge amount of energy, it's very diffuse, it's very spread out. The total energy within our solar system in dark energy is equivalent to 3 hours of sunlight worth of energy. And so it's really hard for it to have any definite effect. It doesn't, push planets around or do anything like that. It's just that the universe is so big, when you add up all that energy, it turns out to be a huge amount. But so far, no really good ideas of how to detect it locally. If you have one, we'd love to hear it.
All right, now we'll go to microphone number 4.
This is about the expansion of the universe, and I'll direct it to Greg. It's a contradiction that probably is only in my mind because I don't understand it, and I'm seeking to find out what the issue is, and that is when we look further into the universe, we look closer to the beginning of the universe, I understand. And as we've done that with Hubble and all the other evidence that we've amassed, the universe seems to be moving faster and faster as it gets further and further away. But aren't we looking further and further to the beginning, and therefore aren't we really saying that it went faster and faster at the beginning and actually is going slower now? Because you're looking at the horizon of the visible universe when you're looking at its furthest distance.
Well, let me see if I can try to help. So there was this very early stage, the Big Bang and inflation that we think went with it, where the acceleration was very fast. Mm-hmm. But then we had things slow down quite a bit due to the mass.
But couldn't it be inflation that we're seeing as what we've called a speeding up of the universe? Couldn't that be the inflation we've talked about, that it was discovered or theorized some time ago?
So there is some idea that what we could be seeing now with the accelerated expansion is something very akin to inflation that got the whole ball rolling.
In the beginning.
But in between, the inflation had to have ceased. The rate of expansion from inflation was so fast that things that we now look upon as being entirely across the universe from each other were once right next to each other. If that had continued, you wouldn't have been able to form galaxies or stars or anything.
Okay. So the evidence is that these things would have happened this way. Thank you.
Let's give everybody a chance to talk, but just to be sure we understand, I know that we're throwing a lot of different concepts around in the course of this evening. That always happens in Berkeley. There are a lot of people who know a lot of things. So when we talk about inflation, we're talking about a period of time, the very, very beginning of the universe. That's a whole nother topic for another night that we can organize as the inflation hypothesis. But now we're talking about things that happened after that very tiny initial period. And dark matter is different from dark energy, but we're not talking about that either tonight. Okay, so we're back to microphone number 1.
So I was intrigued about this notion of the gravitational force kind of leaking out through other dimensions. And we've got other forces. We've got the electromagnetic that apparently isn't leaking out so much, and strong and weak nuclear. And my question is basically, is there any way to experimentally look at something like that? I mean, is that one of these notions that can't even be wrong, or is it something that you could really test and maybe learn something about the universe through?
So that's actually an area where the sort of local tests that were talked about before actually are being carried out and are putting strong limits. So you can do things like ask, Newton's basic prediction for gravity is that it should die off with distance squared, the inverse square law. We can test inverse square law on many different scales, cosmological scales, solar system scales. You expect basically a sort of relation between what's happening on the very largest scales and on extremely small scales, and you can predict exactly what scale it should show up on. So people are doing these inverse square law tests in the laboratory. So you want to get down to sort of micron scales, so well below the scale of an inch, and test, is gravity really an inverse square law there? People are also doing things with lunar laser ranging. They're bouncing lasers off reflectors that were left on the moon in the Apollo program and measuring the distance to the moon very, very precisely and asking, is that changing? These are all ways of testing aspects of gravity. So there are several different ways that people are trying to learn about gravity and do these leaking sort of scenarios, these higher dimension scenarios actually work. So far there's no, I want to emphasize there is no evidence for these higher dimensions. There were just intriguing ideas, and as you say, we can test that.
Okay, we're going to go up to the top, the microphone 2.
The maps that we saw this evening, the background radiation map, the 3D maps of the galaxies that we saw, were not homogeneous. They had hot spots, they had cold spots, they had places where galaxies were looked like they were concentrated in large gaping holes in the structures that we were seeing. Are we expecting dark energy to follow these patterns? And if so, does that allow us to have more likely areas to find them?
So, so far as we can tell, dark energy is not directional or dependent on any density fluctuations. We call those large clusters, large voids. As far as we can tell, if we look at a supernova where Greg will find in the void or at the cluster, they look dimmer in the same way in all directions and in various hot spots, cold spots, as we call. So no evidence of variations on that.
All right, and we're up to number 3.
So as said, time is personal. So you're saying that a star we see every day has already exploded.
I didn't hear the question.
Yeah, I think his question is like the stars we saw, like the supernova we saw, already exploded a long time ago. Is that right?
Yeah, like the beginning of the universe.
Well,
yeah, so some of them, so it depends on how far away they are. But the furthest ones that we've seen exploded 10 billion years ago. So the universe was very different, and the light from them has traveled all that distance when we happen to be at the telescope looking for them. So it's a universe is sort of like a time machine in that sense. Although we don't have any knobs we can twiddle, we can look back in time.
Good. Question over here.
Okay. Well, my question is probably for the theoretician in the group, but if the people that are doing observations have answers, I'd love to hear them. My question has to do with the changing geometries brought about by spatial expansion, universal expansion. One of the points you raised up in your theoretical discussion was that gravity is weak, probably because of differences in geometry between how gravity interacts with a 3D space versus its full dimensional interaction space, that its force lines are spread out geometrically in a different area, and only part of them intersect a 3D spatial area. And my question is, what happens as the universe expands? Because it seems to me that geometries are going to change over time, and that the large difference between gravity and the electromagnetic force lines and the weak and strong nuclear forces are going to come closer and closer into alignment as the universe expands out towards some unimaginable limit. I'd like to get a sense of what the theoreticians think about that.
So there are theories that say gravity is weak because the universe is old. That basically, so it's called running, where basically the strength of the interaction changes as the universe expands. This is one theory. We don't have any particular evidence that this could be right or not. As far as geometry goes, you can think of the blowing up of the balloon that Andy talked about. The geometry, the topology of the balloon, it stays basically a sphere as you blow it up. The geometry itself, in that sort of sense, doesn't need to change as the universe expands. But the strength of the interaction, the strength of gravity, might. We really just don't know.
Okay, thank you.
Here we go to microphone number 1.
Okay, we have an expanding universe, and one of the speakers said it started about 6 billion years ago. Why then? And please keep it simple.
I don't think any of us said 6.
60 billion?
No, the 6 billion came up in my talk, I think, but that was 6 billion years ago was about the time that the expansion started to speed up. The total age of the universe is something like 13.5 billion years, which I really didn't discuss it, but before the discovery of the accelerating universe, this had actually been a real problem because we could find things in the universe that were older than the predicted age of the universe at that time. So the universe people thought was maybe 9 or 10 billion years. We could find stars around in our galaxy that were 12, 13 billion years old. That was a real problem. The discovery of dark energy solved that immediately.
All right, we go up above.
So, Shirley, in connection with Lisa Randall's theory about the leakage of gravity into our dimension and why it's so much weaker than the other forces, couldn't the dark energy explained by the leakage of the greater leakage of gravity outside of beyond where we can see somehow causing the expansion of the universe to accelerate with all this more gravity because more is leaking out that way?
So there are 2 layers of answers to that. I think One is that we haven't seen evidence for it yet, but then there are theories that have suggested it. One of them actually suggested is called the LTB model. It's the Lemaître-Tolman-Bondi model that says if we sit in a void, which means there's less stuff around us, and there's a lot more stuff outside of this void, then maybe the universe can expand that way because of gravity pulling us to those areas. That's actually an active area of research. People will have to figure out whether we can rule this out or maybe this theory is correct.
So your
there's
response,
no evidence for positive or negative confirmation.
So your response is basically that I didn't come up with it.
Wow, sorry.
All right, we'll go over there.
This question is for Eric. I once heard that Leonard Susskind said that the deepest principle of physics is that information is never lost. Does that idea, if it's true, inform you in any way or put any constraints or tell us any information about the physical characteristics of dark energy?
So that's another very active area of speculation for theoretical physics. This idea that information is really the most important quantity, that rather than talking about energy density or entropy, things like that, that it's really the information. And this comes from studies of black holes and theories from Stephen Hawking and from Lenny Susskind. It's often given the name of holography, the idea when you look at a hologram image that even though it's a two-dimensional piece of plastic you're holding, you see a three-dimensional image. But all the information is in those two dimensions. This has been applied with some success to a number of areas of physics. We're still not really quite sure what to do with it. It's a really interesting property in certain systems, but we don't know if it's a sort of fundamental principle or not. But there's a lot of people thinking very hard about that.
And we go down to number 4.
Hi, I was reading something recently that was about people thinking that they might have actually discovered the Higgs boson at the Large Hadron Collider. So I was just wondering, how does that relate to any of this dark energy?
If we do discover the Higgs bosons, that will be a major step forward in confirmation of the standard model for particle physics. But then, is it the dark matter particle? That's a different question. Like, what could be the dark matter particle? We have theories for that, such as things called the WIMPs, the weakly interacting massive particles. They're massive, they don't interact very strongly. But can we actually get them from the RHC? That will be another exciting time for us to wait for.
So the Higgs boson and dark energy, there's nothing really to do with each other?
Not with dark energy,
okay,
as far as we can tell.
All right.
All right, we'll go for another round to number 1.
Penrose and Wilson discovered the cosmic background radiation, and their recent findings that it's not as uniform as it was previously thought. And also, if you look out in the universe with a telescope, you find the star clusters, dark areas, probably with dark energy. So with this expansion uniformly throughout space from each other, you should find the whole universe be evenly distributed. But it isn't so. It's very chaotic. So how do you explain that?
How did the universe get its lumps?
Do you want to?
I'll take part of it. You can take part of it. So the microwave background, the Penzias and Wilson discovery found that the microwave background, so when you see these blue and red spots, you think, oh, it's very lumpy, it's very inhomogeneous. But we've removed all the homogeneous. If we showed the real picture, you would just see a completely uniform color. What you're seeing there is 1 part in 100,000, those little variations. We've removed the 99.99% that is uniform when we show those pictures. So the microwave background is extraordinarily homogeneous. And then do you want to talk about the galaxy distribution?
I was going to mention one more thing, is that what Penzias-Wilson actually saw is like if you turn on the TV back in the old days, the white noise on top, that's actually what the cosmic microwave background sort of like. It's mostly homogeneous, and there are variations, but they are very, very small, as what Eric was saying. And for the galaxies, they grow, they interact gravitationally. So if I have extra stuff here, as I use Andy's word, it's a very technical term, we have extra stuff here, then like the social pressure that Eric talked about, all these other stuff wants to come and join with each other. And so imagine one of those tiny variations, the hotspots, becomes one stuff, and it draws in other stuff into its area, and it forms this city of stars like galaxies like we sit in right now.
Okay, we'll go
Thank
up.
you. I have a question about the integrity of the data, I guess, the signal to noise question. We're measuring all these things from one planet in the edge of our galaxy, looking into billions of years. How confident are we about the accuracy? And you mentioned you're looking for new supernova data. Could that upset the stuff that we already know, or are you just looking for more detail?
Yeah, so it's something that we worry about all the time. In fact, when we discovered this, that the supernovae were 25% dimmer, we certainly assumed that somewhere a mistake had been made in the measurements or in the calculations. So instead of it being just like a eureka moment, there were months of looking through everything to look for mistakes. We've gone well past that, but there's still very subtle things. If we want to go on to making much more precise measurements, there are still subtleties in the data, things that we don't know, because these supernovae, as I described, they're basically bombs. They're big thermonuclear explosions. We're rather lucky that we can work with them as well as we can, but there's still a lot that we don't know about them. And so these are all active areas of research, both for cosmologists and on the supernova side as well, people trying to understand the supernova. And that's true in some of the other areas, although one of the things, for instance, maybe Shirley wants to comment on, for the Baryon acoustic oscillations, it's thought that maybe things are understood more fundamentally. It's not something weird like a supernova, but in these nice pictures that she showed of, a pebble on a pond, something that we can calculate exquisitely well. But we'll see.
We'll go up to number 3.
I'm sorry to take us back to our poor overworked balloon analogy again, but question I was hoping you could straighten out for me. I may be taking it too literally, or maybe I'm just geometrically challenged, but it seems like if there was a singularity and space has been expanding in a spherical way, that we would be able to detect some directionality, that things would not be receding from us equally in every direction we observed, and that we would be able to see more in one direction than another, or more density in one direction than another. So can you explain, do we know where the center of the universe is, and if not, why not?
So you should think of the balloon as the whole universe. So any point on the balloon always sees every other point receding away from it. There is no center on the surface of the balloon. You might say, oh, but there is a unique direction as I go in to the center of the empty space in the balloon. That's a unique point. That's a center. And you can think of it that way, but you have to interpret that radial dimension as time. The universe starts off small from a unique center in time, from a unique point in time, and it's expanding out. But the balloon surface itself is meant to represent all of space. So the center is in time, not in space, is one way to think about that.
All right, and we'll go to microphone number 4.
So you mentioned earlier that this might not be, the identifying dark energy might not actually occur this generation of scientists, but the next. And I'm kind of curious if we all kind of pitched in with an infinite supply of funding and grad students, where would you focus most to try to identify dark energy in your lifetime?
That's a very hard question. I would say that the experiments that we mentioned, for example, like Greg mentioned about the future supernova surveys, or what I mentioned about the future galaxy surveys, like Eric mentioned about the 3D maps, these will all tell us an extensive amount of data that would basically just beats down anything that we have so far. However, I think a significant amount of investment should go into the theory development, not just from the observation side, Because now we have all this data that people will need to come not only analyze them, but also interpret and understand from the theoretical point of view. Can we actually form a theory of, say, everything, if there is one? So as an experimentalist, I would say give me all the money, but I think the real thing is to actually spread it out from theory to observations.
Yeah, the idea of infinite resources is more mind-boggling to us than dark energy.
So Andy, we're going to take one more round of each station, so starting here.
Okay, so we do have time for one more round? Yes. Okay, so our time is almost up, but we'll go around one more time. Let's start over there.
All right. So given the fact that the concept of dark energy is inconsistent with the known empirically provable principles of theoretical physics, are you open to the possibility that dark energy is a paradigm-induced illusion? And when I say that, I mean, so for instance, 500 years ago, people were very intelligent, but they had the paradigm that the Earth was standing still. And therefore, the retrograde motion, right? There is no retrograde motion of Mars. It's an illusion because Earth passes Mars. It would, there's evidence to suggest that what we see as an accelerating universe is actually a geometric effect based on curvature. So in other words, are you open to the possibility that you're chasing something that doesn't exist?
Sure.
So I like that answer.
That really is the thing I was referring to earlier, the Copernican revolution. We have seen this in scientific history. And so in fact, yeah, some people are absolutely delighted that we have all these things that don't fit. And they think, well, it's not just going to be a tweak to what we know, but it's going to be a transformation.
Okay, so
we just don't know what the transformation is yet.
So given that you're open to that, I would suggest that if you Google the name Alex Mayer, M-A-Y-E-R, and that's the first hit on Google, there's some material there that deals with that issue, and I think that almost everybody in this audience would be interested to look at that material. Thank you.
I knew someone was going to get in. Another theory. All right, no one up there? Is there? Oh, how about over here?
I think we're all done.
We're done? So you get the last word.
My question is actually just a simple one. I'm curious if C squared is a conversion factor for energy and mass, right? Then is it still a conversion factor for dark energy and dark matter?
Because E equals mc squared applied to dark energy and dark matter.
Okay, so you can convert energy into mass. It doesn't have to be the same mass. So for example, light has no mass, it has energy. You can convert light into particles with mass, but you're not converting light into light with mass. The same way we think it's theoretically possible to convert dark energy into mass, but the dark energy itself doesn't have mass in quite the same way. It has energy, it has gravity, and we associate gravity with both energy and mass, but we don't have any evidence that it has mass itself.
All right. On that note, let me say that, in fact, one of the most exciting things about doing a panel like this is how few answers we ultimately have at this point. And that just illustrates what I always like to tell my students, that science is a progress report. It's not if you want final answers, ask your guru. But if you want to talk to scientists, you have to accept that it's always a progress report. So we're delighted you could share this moment in science time with us, that you could hear the progress we've made so far. And as we say on the radio, stay tuned. There's more to come. Thank you very much.